Hello, everyone. In this lecture, we're going to begin talking about parametric curves and parametric equations. So this is the first section of chapter 10. Uh, so an important topic for the rest of the chapter. And this stuff will carry over into Calc 3 to some extent. So if you guys are going on to Calc 3, important to know. So what are parametric curves? What are parametric equations? So up to now, we've been thinking of usually function like y is a function of x. So we have y equals f of x, and these functions have curves, right? And we've also dealt with this the other case where we have x as a function of y. Maybe I have x equals g of y. Okay. In both cases, there's certain rules that the curves have to look like, right? So for y equals a function of x, the curve has to pass something called the vertical line test to be a function, right? So this curve, for example, doesn't pass the vertical line test. This is not a function. This is not a function of x. So y is not a function of x for this curve, okay? And if we kind of thought about how this works, we would also see that, well, we don't have the opposite either. We don't have, we can't say that x is not a, we can't say x is a function of y either, okay? So in this case, what is this curve? Is this a function of something? Can we write this as a function somehow? What is going on with this curve? And there's an interesting way to approach this, okay? So instead of trying to think of this as x as a function of y or y as a function of x, let's kind of take a more geometric view of this, or more real world view. Okay, picture this this white curve as a road, and maybe we're up in the air and up in a helicopter, and we're looking down at a road. Okay, so maybe at time 0, I see a car at this blue point. I can think of this as a starting point. And then as time passes, my car moves along the curve. So maybe at time 1, I'm here, and maybe, time 2.5, I'm here, and I keep moving along this curve, all right? So at each time, I'm at a certain point on the road, right? Okay. And each of these points I could think of as x and y in terms of x and y coordinates, right? So at each time t, the car is at some point, okay? And the point we're at really depends on t, right? So like I said, at time 0, we're at that starting point, and time 1, we're here, time 2, 0.5 or whatever, we're here, okay? So really, we can think of these coordinates, the coordinates of our car, as depending on t, okay? In other words, we could kind of picture something like this. The x coordinate depends on t, and the y coordinate depends on t, okay? And maybe maybe we could write these as functions, right? So maybe we could say that x is a function of t, and y is a function of t. So let's say x is f of t, and y is g of t, okay? In our example, that t was time, but in the general scope of section 10.1, this parameter, we're going to call it, might not always be time. As I just alluded to, we're going to call this thing, this t, the parameter. Okay, so basically, what we're dealing with is we're thinking about curves and the xy plane. And instead of thinking of y as a function of x, we're going to think of both coordinates as a function of some third thing, t. We're going to call that t the parameter. And we're going to have these two equations here. X equals f of t and y equals g of t. Those equations we're going to call the parametric equations. So our t is our parameter, and these equations are the parametric equations, meaning like x is a function of the parameter and y is a different function of the parameter. Okay. As we've just seen, we can use these parametric equations to represent curves, and these curves might be simple or complex. The good thing is these curves, as we've seen in this case, we can represent curves that wouldn't normally be considered functions, right? So, for example, remember the circle, right? The circle, very common shape, something we have to work with a lot, but it's not a function of x, right? It doesn't pass that vertical line test. So it's not a function of x. And similarly, it's not going to be a function of y, but it's so common, we'd like some sort of equation to deal with this. We know we have like the Cartesian equation, x squared plus y squared equals 1. That's an equation, it's not a function. Maybe we need some sort of function to represent our circle, okay? And that way we can do all the fun things we do with functions like differentiate, integrate. So we can represent these parametric equations, or we can use these parametric equations to represent curves. These curves might be very simple or they might be complex. So parametric equations, as I said, we can use them to represent things that aren't normally functions, but maybe we have a set of parametric equations and they represent something really simple. They could represent something as simple as a line or a parabola. So the curves these parametric equations describe, they might be simple, they might be complicated. So in order to get an idea of what's going on when we have a system of parametric equations, usually what we do is we graph the parametric equations in the xy plane. So the xy plane, the plane we usually work with, we would call that the Cartesian plane, and like a pair like this would be called Cartesian coordinates. Just a little lingo for you guys. So maybe I want to graph my parametric equations in the Cartesian plane. How do I do that? I just make this table, as you see here, okay? And what I'm going to do is I have these equations, right? X equals maybe a function of t and y equals a different function of t. So how do I graph this? First thing I do is I make a table and I just pick a bunch of t values. Okay, so maybe I pick 0, 1, 2, 3, 4. And then I take these t values and I plug them into my functions. Okay. Okay. And then what I end up doing is once I have this table of values, I just plot these points together. Okay. So let's do a quick example. So let's think about this system of parametric equations. Okay. So I have this system of parametric equations. I have x equals 2t and y equals 4t. Let's try and graph these parametric equations. Okay. So the first thing I'm going to do is I'm going to make my table, and I'm going to pick just some t values, any t values I want, since I'm not given any restrictions here. Maybe sometimes they'll give us restrictions on t, like t is between 0 and 4 or something like that. Other times we can just pick whatever t values are convenient. Okay, so let's pick some t values. Okay, I'll start with like -1. Okay, so if t is -1, what is my x coordinate? X would be -2. What would be my y coordinate? -4. If t is 0, x would be 0, y would be 0. If t is 1, I'd have 2, 4. If t is 2, I'd have 4, 8. And then if t is 3, I'd have 6 and 12. Now let's just graph these xy points and see what we get. Okay, if I graph -2, -4. Maybe that'd be somewhere down here. And then I graph, let's see, 0, 0. That'd be there. Then I graph 2, 4. Let's do this in like green. Okay. Boom, boom. I graph 2, 4. Maybe that'd be here. And I graph 3, 6. Maybe that'd be there. And then I connect the dots. That's all I do. And I see I get this nice line. Okay. Oh, okay. But the thing that's different, like you might be asking, all right, so I just got a line. I could have just done that with an equation of y, like y equals 2x in this case. What's better about parametric curves? Okay, well, parametric curves, as I said before, we can do more complicated curves with parametric equations. But parametric equations also have this idea of direction. Okay, so I could think of as I said, I could think of this as like describing a car moving along a road. Which direction is the car moving as time passes? Well, as t increases, what's happening? So at time 0 or parameter 0, t0, I'm here, right? I'm at the point, let's do it in like red now. I'll do yellow. So at time 0, I'm here at this point, right? And then I increase my time. I go up to t1, and where am I? I'm here. Or actually, it'd be more like somewhere in the middle, right? Okay. Oh, no. Oh, no. Yeah. So at time 1, I'm here. Okay. At time 1, I'm here, but the x and y coordinates would be 2 and 4, right? Okay. So to reiterate, at time 0, I'm here. At time 1, I'm here. So as t increases, I'm going this way. If I think of this as my road, I'm going this way. So these parametric curves have a direction built in that normal Cartesian curves don't. So if I just had the equation like y equals 2x, okay, that line looks very similar to what we just saw, right? It looks something like this. But what direction, if I'm at a point on this line, if my car is moving along this line, what direction is it going? Well, there's nothing from here that indicates what direction my car would be going, my kind of mental car. It could be moving this way along the line, or it could be moving that way along the line, okay? But these parametric curves have the idea of direction built in, okay? So as t increases, we see we're moving this way. So that's a cool little thing about parametric curves. And let's start looking at slightly more complicated curves. Let's look at this example. Let's say we have these two parametric equations, x equals cosine of t, y equals sine of t, and we have this restriction on our t, like I said, we might see. So t is between 0 and 2 pi. Okay, so let's graph this. Okay, so I know my t needs to be between 0 and 2 pi, so let's start with 0. At time 0, my x is cosine of 0, which is 1, and y is sine of 0, which is 0. Okay, then let's do pi over 6. At pi over 6, okay, my x would be square root of 3 over 2, and my y would be, what, 1/2. At time pi over 4, let's see, I'll get square root of 2 over 2, square root of 2 over 2. At time, let's jump to pi over 2. I'm at 0, 1. let's see, how about jump to pi. At pi, I'm at what, -1, 0, 3 pi over 2, I'm at 0, -1, and then we'll do 2 pi. At 2 pi, we're at 1, 0. Okay, so this should be enough points to get an idea of what's going on. So let's graph these points, and I'll do them in green again. So let's start at time 0. At time 0, I'm at the point 1, 0, which we'll put here. Okay. And what about at time pi over 6? We'd be at square root of 3 over 2 and 1/2, which would be something like here. And then let's go ahead and jump to pi over 2. At pi over 2, I'm at x coordinate 0, y coordinate 1, so I'd be up here. Okay, and then let's see, at time pi, I'd be at -1, 0, so I'd be there. Then I'd go for 3 pi over 2, I would be here, and then at 2 pi, I'm back here. So maybe, just from the 4 or 5 points I've drawn, maybe you think it's like just a diamond or something. Okay, so this is a balancing act we have to have. We have to have enough points to get a clear idea of what's going on. So if I just drew a bunch of points, I get a more accurate picture of what's going on, right? So if I drew a bunch of points, I'd see, my curve is actually a circle. And I've drawn a bad circle, but let's pretend this is perfectly circular. Okay. And which direction am I moving? Well, I started at time 0, I was here, right? And then I started drawing my points in this direction as t increased. Okay, so I have this circle that's looping around this way. And then at 2 pi, I've arrived back at the beginning, back at the origin, or back at starting point. Okay, so my curve looks like this. Now, word of warning that different parametric equations can give the same curves, similar curves, and sometimes the exact same curves. So what about x equals sine of 2t, y equals cosine of 2t? Okay, this would be the same circle. I'll invite you guys to do this on your own. This should give the same exact circle as this thing, but it should be going in the other direction. Okay. So let's see, what should this look like? Excuse me. This should be a circle. Let's see, where would it start? It would actually start up here. And as time increased, which way would it be moving? Moving this way. Okay. So it would be a circle going around this way. And try this for yourselves, but it should make, let's see, at time 0, it should be here. And then I believe at time 1 pi, it will have made one full loop. Okay. Whereas in our previous example, it made one full loop it took 2 pi to make one full loop, right? Okay. So try this one on your own, see what's the similar and different about this example. Okay. X equals sine of 2t, or y equals cosine of 2t. Okay. Now, if we are given parametric equations, sometimes we've seen sometimes these parametric equations. So we had an example where the parametric equations just represented a line, right? Well, a line, as we said, we can just write we could have written that as y equals a function of x, right? We could have written, I believe our line was y equals 2x, right? We had the parametric equations, x equals 2t, y equals 4t, you know. And then once we graphed them, we saw, okay, well, the graph ends up being the same thing as y equals 2x. So if we have a case like this, where we could have just as easily written as a function of y, can we convert? Can we take these parametric equations and convert them into a Cartesian equation? Okay. When we have y equals a function of x, or x equals a function of y, those are called Cartesian equations, meaning we've written them, the points are, let's see, well, it's just y is a function of x, or x is a function of y. Those are Cartesian equations. Trying to think of why they would be called, you know, good reason to call them that, but it's just the y is a function of these Cartesian coordinates are one's a function of the other. So as I was saying, maybe we have parametric equations and we want to convert to a Cartesian equation. Okay, sometimes we can do that. So sometimes we can do that. We can't always do that, right? Like as I alluded, or as we've seen, right? The parametric equations, and we've seen two examples now where we got a system of parametric equations and they give us a circle. But as I alluded to, okay, we can get Cartesian equation. We can get a Cartesian equation for this. It might not be a function. Okay, we should be able to get a Cartesian equation, but it might not always be a function. The process that we use to take parametric equations and convert into a Cartesian equation, that's called eliminating the parameter. So essentially what we're going to do is get rid of the t and write like y as a function of x, or x as a function of y. So let's look at the procedure. In general, let's say I want to write y as a function of x. So let's say I want to write y equals h of x. How do I do that? How do I go from these to here? Okay. The general procedure, this isn't going to always work, but the general procedure is to solve for t in this first equation. Okay. So you want to rearrange it so you get something like this: t equals blank. Okay. And then you're going to take this blank and plug it in for t in this second equation. Okay, and then you should have y is just a function of x. So let's try it. You know, it might be a little weird to think about abstractly, so let's just try it. So let's say I have x equals e to the power of 5t and y equals t plus 8. And I would like to write this as a function like this: y equals a function of x. Okay. So my procedure, as I said, was let's start with this and let's try and solve for t. Okay. So the first problem is that t is up in the power, right? I want to bring that out of the power. How can I do that? If I take the ln of both sides, what happens? Well, remember, when I take the ln of e to some power, that becomes just 5t, right? The ln and the e cancel. And then if I want to get t by itself, I would divide both sides by 5. Okay, so I have an expression for t now. So now I'm going to take this expression for t, I'm going to plug it into the equation y equals t plus 8. Okay, so let's replace this t with this thing. So now I have y equals ln of x over 5 plus 8. Okay, and now I'm done. I've written y as a function of x. So I've eliminated the parameter. We have to be careful though, because ln of x is not always defined, right? It's not defined for negative numbers. So we have to take that into account. I'll probably cover that more in the problem video. Well, I'll cover it a little bit in this next example, actually. We could also eliminate the parameter and write x as a function of y. So in this example, I wrote y as a function of x, but maybe that's not the right thing to do. That won't always be the right thing to do. So maybe I want to write x as a function of y instead. So let's look at this example. X equals t squared and y equals t cubed. And let's say we're not even told which parameter we should solve for. Let's say we're only given these instructions. Eliminate the parameter to write as a Cartesian equation. Okay. As I said earlier, a Cartesian equation is something like x equals function of y, or y equals a function of x. Okay. So we need to take these and convert into one of these. Okay. So the question is, which one is is one better than the other? In some cases, either way would be acceptable. We could write it as a function of x as a function of y, or we could write y as a function of x, and either way would work. Okay. So in that example we had where we had x equals, let's see, 2t, y equals 4t. We could do this one either way, right? We could say, let's see, okay, we could solve for y equals 2x, or we could do it in the opposite order, and we could solve for, if we solved it the other way, it would be, okay. So both of these give a valid answer. Okay. Now the question is, do both of these, if I'm now looking at this problem, could I solve this one either way? That's a bit more complicated. And really, it depends on our range of t's. So for example, let's say we had t is between 4 and -4. Okay. So let's say in this problem where we were also given the condition like this. All right, let's first think of what this looks like. Let's try and graph this. These parametric curves. Okay, so let's see if I have t is -4. Let's see if I plug that in, x would be 16. That'd be way over here, and then my y would be what, -64. So that'd be way down here. Okay, and then let's see at 0, at t equals 0, everything would be 0. So it'd be up here. And let's see, it'd be some kind of curve like this. And then let's see, as t goes to positive, okay. If t goes to +4, then we'd have 16 and be up here 64. Okay. So my curve looks something like this. My parametric curve looks something like this. And as t increases, it's going this way. And now that we've graphed it, maybe it's clear, right? This thing doesn't pass the vertical line test. All right? So I can guarantee that y is not a function of x. Okay? So that means if I write this as a parametric equation, I should do it the other way, right? I should write x as a function of y. Okay? So let's see, I have on my original t squared and t cubed. So then my process should be the opposite of the previous example. In the previous example, I solved for t in terms of x, okay? So in this example, I'm gonna solve for t in terms of y. So I got y equals t cubed. I'm gonna solve for t. So cube root of y equals t. Now I'm gonna take this and plug it into my equation for x. So I should have x equals cube root of y squared. In other words, x equals y to the 2/3. And this should be my final answer. Now, the situation gets a bit more complicated in that, you know, this, I would say this way is always safe, okay? But if we had been given the same format, x equals, what was it, t squared, y equals t cubed, but we were given, let's say we were given for t between 0 and 4. What would the graph of that look like? Oh, excuse me. Well, the graph of this thing would just look like this. Okay, so this is a function of x, right? You know, it passes the vertical line test. Okay, so then I could do this one either way. I could say square root of x equals t, and then plug that into y and get, well, y equals square root of x cubed, so y equals x to the 3/2, okay? Or I could have done it the other way and get that x equals y to the 2/3. In this case, either one would be acceptable. So a bit confusing there. I'll talk more about this in the problem video about which one to choose. But we can solve these sometimes either way. For a general guideline, if you're asked to eliminate the parameter, what would I do? I would look at both of the parametric equations. Okay. And think about solving for t in both. If solving for t could be undefined in one case, solve the other way. Okay, what do I mean by that? So in this case, in the previous case, we had x equals t squared, right? And y equals t cubed. Well, if I had looked at the first equation, this would give me a hint about the way I should solve this. If I had looked at the first equation, x equals t squared, and I tried to solve for t, okay, really what I would have would be plus or minus square root of x equals t. So that's kind of undefined, right? That's kind of ambiguous. Okay, so that tells me I shouldn't attempt it this way. I should instead solve for t in this equation. Okay, if I take the cube root of y, that's always defined, right? It's unambiguous, right? I can do this for positive numbers, I can do it for negative numbers, and it gives me a single answer. Like there's no positive negative sign out here, right? On the other hand, let's say I had we had an example like this earlier, and as I alluded to in that problem, you know, it really depends if this is acceptable or not. It really depends on what's going on with the t. So maybe we will see a better way. You know, I did this one way earlier, but let's see if maybe there's a better way. Okay, so I try and solve for t in this, and what did I do? I did ln of x equals 5t, right? Okay, but what if x is negative, right? Ln of negative numbers is not defined, so this could be undefined, right? So maybe that's a hint that, well, I should have done it the other way. Maybe what I should have done was y minus 8 equals t over here, and then take this and plug it into my other side. Okay, so maybe I should have done it this way. Okay, so that's one way to think about it. I would look at both equations and see, okay, if I solve for t in this left side, is everything going to be defined? If not, I would do it the other way. So a little bit of a rambling explanation there, but hopefully clear things up in the problem video. So what have we seen? We've seen, okay, if x equals a function, if we have these parametric equations, we can sometimes convert to a Cartesian equation, like x equals h of y. Okay. Can we do it the other way? Can we go from an equation like this to parametric equations? Yeah, I don't think it's going to come up because it's really trivial. It's really easy. Okay, so let's say I have y equals x squared, and I want to convert to like x equals f of t, y equals g of t. Okay. How do I do that? Well, if I have like y equals f of x, or let's see, let's use a different letter. Let's say I have y equals h of x, and I want to convert to something like this. Okay, it's easy. Whatever's in the parentheses here, I say x, I just say x equals t. Okay, and then what would y? Y would be h of t. Okay, so that might be confusing, but let's say I have y equals, let's say I start with this equation, right? And I want to convert to parametric. Well, I could think of this as, you know, a function of x, right? Well, x equals, I'll say x equals t, and then y equals f of t. So what should my f of t be? That would just be 7t cubed plus 4. And now this is a parametric equation that it's the same thing as this. It gives the same curve. Okay, so converting from Cartesian to parametric is really easy, and it's so easy. I don't think your homework will even ask about that, but I'll double check that before the problem video. So that is all for this, and I will publish the lecture video for 10.2 later today.